what happens if you have a general situation with all sorts of irregularities? And that's what Stephen Hawking looked at. Later on we got together and wrote a paper on this together. But most of the work on this end was done by him, developing the arguments which I had used for the collapse of black holes. Now, I began to worry about this because what happens in a general collapse? You see, here is the very symmetrical Big Bang. Why is it going to be symmetrical? Why not irregularities? Well, what happens in this collapse? Suppose we imagine a collapsing model of the universe with time still going upwards, and there are irregularities. Now, these irregularities will cause black holes. These black holes will congeal with each other, provide bigger and bigger black holes, more and more terrible singularities, an enormous mess of a singularity, nothing like the kind of thing we saw at the beginning. You have an incredibly complicated, and this is where the Russians also now corrected their mistake and found that in general you did get very, very complicated singularities in the future. Now, what is so different from that, whereas in the past we don't get the time reverse of what we expect to see in a generic collapse in the future, the great mess that you see in this picture here, you get something very regular, which is apparently what we see. Now, what is the difference between the situation in the future and that in the past? Well, mainly it's because something called the Weyl curvature dominates in the future and doesn't in the past. Here I have a picture, somebody at the future of this picture looking back. This is the past light cone of a point, and the light rays become distorted by the presence of Weyl curvature and presence of Ricci curvature. That's, according to the Einstein equations, the Ricci curvature is what's created by the matter, and the Weyl curvature is what is the free gravity. So the gravitational field is described by this Weyl curvature, and the matter is described by the Ricci curvature. Now, the Ricci curvature is a sort of regular inwards focusing in all directions, whereas the Weyl curvature gives you this great distortion. And what seems to be the case is that in the remote future, one has a dominating Weyl curvature, whereas the Weyl curvature seems not to be present in the very early universe. Now, this is very much related to the second law of thermodynamics. Now, here I have a picture of how the second law of thermodynamics operates. The top three pictures describe, say, a gas in a box, where we have a smaller box and all the material is constrained into this little corner. You open up the box and it spreads out through the box. So from left to right, we see the increasing of time and the increasing of entropy, and we get a much more uniform situation as entropy increases. So that's the way ordinary matter seems to behave. But how about gravity? In the bottom three pictures, we have, on the left-hand side at the bottom, we have maybe imagine a very big box, of a galactic scale box with many, many stars. Initially, you might imagine they're all uniformly spread out, but as gravity starts to operate, they clump together and form clumpy distributions, and finally you get collapsed into a black hole where the entropy goes just shooting up enormously. So as entropy increases with gravity, the irregularities increase, whereas with ordinary matter, you expect the uniformity to be the situation with increasing entropy. So the real puzzle is, why is it that in the very early universe you see uniformity, which was consistent with very high entropy, but on the other hand, very low gravitational entropy. Very high entropy in the matter, and that's what we tend to see, but very low gravitational entropy. And I thought this was a great puzzle. So I formulated a sort of hypothesis that for some strange reason, the singularities in the future had to be zero Weyl curvature, whereas the singularities in the past had to have this zero Weyl curvature, whereas the singularities in the future, the Weyl curvature could absolutely go wild and dominate. And I, like everybody else, seem to think this must be a feature of quantum gravity. You see, when the curvatures get very, very big, then you start to imagine that quantum effects will start to play a role. It's not just classical Einstein theory. When the radius of curvature becomes so small, maybe say 10 orders smaller magnitude than the radius of a proton or something like that. It's the sort of scale in which you might expect that you have quantum gravity playing a big role. But what's so strange about it is, if this is the case, why is it that the quantum gravity seems to behave so differently from the past type singularity, where the Weyl curvature seems to be zero or very close to zero, whereas in the future singularities it seems to dominate and go crazy? Now, for a long time I seem to think this must be a very strange kind of quantum gravity, where gravity is changing the very structure of quantum mechanics. Now, I do actually believe that. There is a great puzzle about quantum mechanics, which is called the measurement problem, which is not really explained in standard quantum mechanics. And it is my belief that when you bring gravity in, it's going to resolve that problem. So for a long time I thought, well, this very strange quantum gravity, where gravity behaves very differently from everything else, maybe that's the explanation. But then I had a different idea. It's really very hard to make that work, and I certainly was not able to make it work. Let me go back to the picture of the light cone. And now let me make it a little bit more complete. You see, that picture just described the light cones, the null cones. It did not describe how time behaves in general relativity. You see, time features. Here we have two of the most famous formulae of 20th century physics. There's Einstein's E equals mc squared, of course, and also Max Planck's E equals h nu. Max Planck's formula tells us that energy and frequency are equivalent. Einstein's formula tells us that energy and mass are equivalent. Put the two together, that tells you mass and frequency are equivalent. So when you have mass, you have automatically a frequency. So every mass is a clock. So when you want to bring clocks in, the rate of time, that's what mass does for you. If you have no mass, you wouldn't have clocks. But if you do have mass, that determines these little hill and bowl-shaped surfaces that I've introduced into the light cones tell you the ticks of a clock. And here we have two particles whizzing at different speeds, but they're related by these surfaces which tell when the first tick happens, the second tick, and so on. But if you just had light-like particles, in other words, photons and things like that, who don't notice these surfaces at all, they don't register the passage of time, particles without mass don't even know about the passage of time, they only know about the light cones. So this was a remarkable thing, which seemed to me to be important. It's also true of Maxwell's equations, which describe the classical behavior of light, and these equations are completely insensitive to the scale. They just care about the light cones, they don't care about the scale. Now what happens when you just have the light cones? You don't have the scale, but you massless particles, things without mass, that's what they're interested in. Well, it's very interesting because when you don't have any scale, you can consider a kind of geometry which is called conformal geometry. Conformal geometry is the geometry of small shapes, if you like, of angles. And here we have a lovely picture due to the Dutch artist M.C. Escher, where he shows with a certain type of geometry, it's called hyperbolic geometry, don't worry about that. But the important thing about this geometry is that you can represent infinity. This circular boundary to this picture represents the infinity of these creatures. So the creatures in Escher's picture, they don't feel the boundary there. The mass keeps them, so they actually know where they are, if you like. They know how big they are. But if they were massless, they could go right out to the boundary and they wouldn't notice any difference from anywhere else. If they were photons, the photons could probe the boundary and go right through and seem to explore some world outside infinity. Very strange idea, but if there were no mass, that's the sort of picture which makes sense. So I began to think about this, and when we talk about the whole universe, it was discovered at the turn of the century, more or less, that there is something, sometimes people call it dark energy. I call it Einstein's cosmological constant. He introduced it in 1917 for the wrong reason, nevertheless, but it seems to be the best explanation for what's happening in the remote future. Here we have a picture of the universe in its expansion. The remote future is this exponential expansion where this dark energy or cosmological constant seems to dominate. And we have the Big Bang at the bottom of the picture. And the feature of this is we can apply the trick that Escher used in his picture and squash down infinity and make it into a finite boundary. If you only have photons running around, then they won't notice the difference, and you can squash it down into a finite boundary. What about the Big Bang? Well, the idea is you can stretch that out into a finite boundary as well. You might worry, well, there's a lot of massive particles running around at the Big Bang, so surely they know how big the universe is. No, they don't really, because it's so hot, so dense and so hot at the Big Bang that they rush around so fast that the mass of particles becomes completely irrelevant. And again, you have a situation where, in effect, everything is without mass. It's not actually without mass, but the mass is so unimportant at the Big Bang because the energy is so big that the energy of the particles is in their motion, according to Einstein's theory, in their motion and not in the mass of the individual particles. So they behave like massless things too. So you can apply the trick at the beginning and stretch out the Big Bang and make it into something nice and smooth, and you can squash down infinity and make it something nice and smooth. Now the advantage about this is that you can only stretch out the Big Bang and making it smooth in very, very special circumstances. My former student and colleague Paul Todd used this as rather than using my Weyl curvature hypothesis, saying the Weyl curvature is zero, a better way of doing it was to say you could stretch out the Big Bang and make it nice and smooth. So I liked his way of doing it. It's a much better way. And moreover, you can do something more. You can say that the remote future, well, is that the end? Or can you imagine that the remote future extends into something else? What about the Big Bang? Maybe you can imagine that extends backwards into something else. So this was the picture that, modifying Paul Todd's idea into one where the Weyl curvature is actually zero at the beginning and not just finite as he had. You can imagine that this Big Bang was actually the continuation of something before. So I'm saying that why the Big Bang was so special was because it is the conformal continuation of something, the remote future. You might say this is very hard to imagine, because how could something so cold and rarefied in the remote future be physically like something so hot and dense? But when you think about it, it's not so strange, because when you have no mass around, it can't tell the difference between big and small, it therefore can't tell the big difference between hot and cold. You see, when you squash down this very rarefied remote future, it becomes hotter. When you stretch out the very hot and dense Big Bang, it becomes colder. And they seem to match. So the model I'm putting forward, a crazy model, but nevertheless, it seems to make a lot of sense. That you stretch out the Big Bang, and then it becomes the continuation of the remote future of a previous eon. So in this picture, what we used to think is the entire universe, the Big Bang being the beginning and the remote future being the end, I'm saying that this is just one eon, one stage of a perhaps infinite succession of eons, one after the other. Now, it's also, you see, when I first thought of this idea about 15 years ago or so, I thought I'd go and lecture about this forever. Nobody will ever be able to contradict me because there's no observations against it. But then I thought, well, maybe there are observations, because signals can get through. If these signals are light signals, if they, more importantly, are gravitational signals, they can get through. And I thought about if you have collapse, if you have black holes which spiral into each other and huge galactic scale black holes. I'm not talking about the ones that LIGO sees, and we certainly see black holes running into each other, but the black holes at centers of galaxies, absolutely enormous ones, eventually will start to spiral into each other and produce signals which maybe we could see. There are also other effects which we can see, and it seems to be the case that there are signals that we are seeing in the early cosmic microwave background which are explicable, and only explicable as far as I can see, in terms of something going on before the Big Bang, which is consistent with the picture which I've just been showing you. It's something for the future to see whether these things continue to support this idea, or do we see effects which contradict the idea. I think it's very exciting because it opens up new things in cosmology which hadn't been thought of before. Thank you very much.